The next topic we need to discuss is something called trigonometric integrals, which seems very vague in its title, but it really deals with two specific types of integrals. This type, where we have sine raised to a power x times cosine to a power x, and this one with secants and tangents, secant to a power times tangent to a power. And so this isn't necessarily a very wide-reaching technique, but it's a way we can integrate each of these different types of integrals. So it stems from something you would have learned all the way back in Calc 1, which would look something like this integral here. And it's a basic substitution idea. And so in this example, you have sine times cosine. So we're looking at this scenario where sine is raised to a power and cosine is raised to a power, but it's the first power. And that's the key. One of the two of these functions is raised to the first power, which allows us to very easily use u substitution. So if I were to let u equal sine x, and you got to remember all the way back to trigonometry that sine to the fifth x is the same thing as sine x all to the fifth, right? It's not the same as sine x to the fifth. Okay, so you got to recognize the differences there. All right, so that being said, what we have here is a simple u substitution. So u equals sine x, du equals cosine x dx. And this integral becomes u to the fifth du. Again, sine x dx is du, cosine x dx is du, and sine being u becomes u to the fifth. So if it's just u to the fifth du, that's a very easy integral to evaluate. That would be u to the 6 over 6 plus c. Resubstitute in sine in for u, and you end up with sine to the sixth x over 6 plus c. So, pretty simple integral. But the reason why it's simple is because the cosine was to the first power. And that's the trick. I could do an integral that looks very similar, but switch the roles of sine and cosine, have cosine to the fifth x, and then sine to the first, and the same thing would happen. I'd have my u, this time u would be cosine, du would be the sine, and we would make it work out very similarly. But what if I gave you this integral? Sine to the fifth x times cosine to the second x dx. Now we have a problem. And the problem that we have here is that cosine is to the second power. And if I let u equal sine x, and my du is cosine x dx, that's not going to work out with this integral. So how am I going to make that work? Where sine and cosine are both raised to powers other than 1. If either of them is to the first power, then it's very simple to do. If both of them are not raised to the first power, how will we get it done? Well, this isn't going to work. What we're going to try and do is turn this integral into something that works out very similarly to this one, or the way we got that one done, and just end up trying to do a power rule in the end. So that's the technique, how we get that done. And then we'll do the same thing with the secant and tangent integrals. One way to approach this whole section is to just give you a series of formulas and say this is how we're going to do all these integrals, and it'll make you memorize about 10 or so formulas to get the job done. But the reality is nobody's going to sit there and memorize these 10 formulas to do these integrals. It's just not realistic. It can be done, but it's not realistic. So what we're going to do is we're going to learn how to do it based off of what type of powers we see. And I like this better because it gives you an understanding of why the formulas would even work in the first place. So there are three identities we're going to be working with here. First off, you have what we call the Pythagorean identity. Everyone knows this one. Sine squared x plus cosine squared x equals 1. Then we have these other two identities, which we're going to call the power reducing identities. And so sine squared equals 1 minus cosine 2x over 2, and cosine squared equals 1 plus cosine 2x over 2. These are variations of the double angle identities and therefore also the half angle identities, but we would refer to these as the power reducing identities. And the reason we do that is because it takes a sine squared and converts it into a cosine to the first power, and a cosine squared to a cosine to the first power. The only difference between them is which one has the minus and the plus. Sine minus cosine is the plus. All right, so those are the identities we need to get this done. So here's how we're going to do it. These are the guidelines we're going to go through. First off, we look at the powers of the sine and the cosine. So m and n are those two different powers. M would be the sine's power, n would be the cosine's power, or vice versa. It doesn't really matter. Sine and cosine. So let's just say the power for the sine is odd and positive. Okay? So if the power for the sine is odd and positive, what we're going to do is we're going to save a sine factor for the du and convert everything else to cosines. Well, how does that get done? Well, think about it. If sine is to an odd powers can be written as 2k plus 1. The idea is 2k plus 1 is the way you always can write an odd number. It's an even number plus 1. Okay? So we could write sine as sine to the 2k plus 1. Cosine is to just some random power. It doesn't matter what it is. Even, odd, positive, negative. Doesn't matter. So cosine. But sine's to an odd power. So what we're going to do is we're going to take that and we're going to split it apart. We can write, if you say you had a to the 2k plus 1. You can write that as a to the 2k times a to the first. Because if you multiply the bases, you add the exponents. So I'm going to write this as sine to the second power to the k and sine to the first. Because also remember that 2k can be squared to the k. Because when you have a power to a power, you multiply those exponents. So I'm going to break this sine to the 2k plus 1 into sine squared to the k and then a sine to the first. Now, what am I going to do here? Well, what I'm going to do is say this is going to be my du. Well, if that's going to be my du, why? Because it's to the first power. What is that the derivative of? Well, sine is the derivative of cosine. Now we're off by a negative there, but generally as a function, you differentiate a cosine, you get a sine. Okay? So what we need to do is to say, well, that means the rest of this integral here has to become cosines. And we have it here, so this has to be converted to cosine. Once we do that, we have a bunch of cosines, which will be my u, and then we have the derivative, which would be my du. So how are we going to get that done? Well, the way we get that done is we use the Pythagorean identity here. Sine squared equals 1 minus cosine squared. So I just make that conversion there. So now I have a bunch of cosines. I could let u be cosine. Du is minus sine x dx. Now it's minus, but sine x dx is the important part. I could always flip the negative over to the other side. And I have my u's to different powers, du. And it looks a lot like that previous example we just gave. So that's if sine is to an odd positive power. Another option is if cosine is to an odd positive power. Well, this basically works out the same way. We're going to save a cosine factor for the du, we'll convert everything else to sines, and we'll integrate. So same idea. Cosine is the 2k plus 1, you see that there. Sine is just some random power. We're going to split that 2k plus 1 into a cosine squared to the k, and then a cosine to the first, just like we did with the sine in the previous example. And here we use the Pythagorean identity the other way, where cosine squared equals 1 minus sine squared. So now we have this saved for my du. So here's my du. And all these things that are left are sines, which will be u to different powers. So we have u's to powers and then the du. So same idea in this case, your u ends up being sine x, and your du ends up being cosine x dx, and you work it out that way. Again, much like the first example we did. Someone always asks, well, what if both sine and cosine are both to odd positive powers? Which is a possibility. Both of these powers are odd and positive. Well, then it actually doesn't matter which way you do it. Pick one, okay? Either pick it by saving a sine for the du or a cosine for the du. Whichever way you do it, you'll get the right answer. More times than not, this textbook that we're using would do the sine first. So if you want your answer to look exactly like the book's answer, I would do that. Ultimately, it doesn't really matter. What you'll see is that when you choose one or the other, when both are appropriate, your answer may look a little different. Your answer will be in terms of cosines or in terms of sines, depending on which one you choose. It doesn't mean that the answer is wrong, it's just a different form of the same answer. Something you've seen in trigonometry is you can write a trigonometric expression 2, 3, 4, 5 different ways. They all may look different, but they all are equal to each other. And that's something that would happen here. All right, third scenario. Let's get rid of all this. I don't want to look at this anymore. Third scenario. What if powers for both sine and cosine happen to be even or non-negative? Okay? So you have no odd powers. So the key to doing these problems is first, do you have any odd powers? The second you have odd powers, 1 and 2 essentially come into play. But if you don't have any odd powers, okay, what you're going to want to do is you're going to want to use the power reducing identity. So if you have even powers, even can always be written as a square, and a square can be reduced by using one of these two identities. And so what we're going to do is we're going to keep reducing and convert the integrand until eventually we get to odd powers, and then we'll proceed to number 2. Because it'll be number 2 because both of these convert to cosines. So eventually we'll have a cosine to an odd power and be able to do it this way. This one is probably the most time-consuming one of all, depending on how big the even power is. And so we need to see some examples. I think the more examples we do, the more this will make sense for you. So here's a prime example. Very similar to my first example, except for right here. That's the big difference. And that makes all the difference in the difficulty level of this problem. Okay. So what we see here, though, is we have sine to an odd, cosine to an even. So we're going to focus on the fact that sine is to the odd power. So what I'm going to do is I need to pull one of these signs out and save it for my du with the dx. Okay? So I'm going to rewrite this integral as sine squared x cosine to the 4th x times sine x dx. Still, sine squared and sine, that's sine cubed. This is no different. But I'm doing this so that here, this is being saved for my du. Well, if that's going to be my du, my u has to be cosine. Well, I need to take everything that's left here and make all this cosine. And that's where the Pythagorean identity comes into play. So I do the Pythagorean identity, which is 1 minus cosine squared x times still the cosine to the 4th x sine x dx. What I like to do here, and it's not necessarily, but it'll have to be done eventually, so I like to do it now, is I'll distribute this cosine in here and here. So cosine to the 4th, let's see if we get that to work. Cosine to the 4th x minus, this will become cosine to the 6th x times sine x dx. And again, I save this for the end on purpose. So now my u is cosine x, my du is sine x dx with a negative, right? It's always a negative. So I'll have to flip that negative to the other side. So now it's over here. But all that happens is I end up getting u to the fourth minus u to the sixth, and sine x dx is du times a negative, so that'll just throw a negative out in the front. And so I just basically have two simple power rule integrals. So I have this negative out in front, I get u to the fifth over 5 minus u to the seventh over 7 plus c, resubstitute in. I can distribute this negative in as well, and I get negative cosine to the fifth x over 5 plus cosine to the seventh x over 7 plus c. The end. So that little technique of saving a sign for the end is how this whole thing works. But that can only be done if sign was to an odd power in the beginning. Here's another one. In this example, let's ignore the pi thirds and the pi sixths for right now. That's just evaluating. It's just going to get real messy at the end, which is fine. We'll do it. But we're really going to focus on the integration of this. So what do we have? We have cosine to an odd power and sines to the 1/2 power, right? That's what that square root is. And it's in the denominator. So when you look at this, the thing I'm focusing on is not the sine power. That's got too messy. I'm looking at the cosines to an odd. That's the big focus here. So I'm going to rewrite this. First off, I'm going to bring sine up to the numerator, so now it's minus 1/2 power. I'm going to peel one of these cosine powers off, so now it's cosine to the first times cosine squared. And I'm going to save that for my du. So now I'm looking at all this. Well, if this is du, then u has to be sine. So this cosine squared has to be converted to a sine, and I'll do that simply with the Pythagorean identity. So I have sine to the minus 1/2 x. This will be 1 minus sine squared x, and then I still have that cosine. If my pen will work, I have that cosine x dx. There we go. All right, so now, again, we don't have to do this, but we will. I like just doing it now. Distribute this in here and here. So I end up with sine to the minus 1/2 x minus sine to the minus 1/2 times sine squared would give me sine to the 3/2 x. Remember, you have to add those exponents together. And then I have the cosine x still sitting here waiting. So it's all set for me to say u equals, let's erase that, u equals sine x, du equals cosine x dx, and I simply just get u to the minus 1/2 minus u to the 3/2 du. Again, can't get much easier than that, right? So what are we going to do now? Power rule. Add 1 to the power, divide by, right? So I'm going to get 2u to the 1/2 minus 2/5 u to the 5/2 plus c. Substitute your u back in here and here, and we are done. So 2 sine to the 1/2 x minus 2/5 sine to the 5/2 x plus c. Done. It's a little messy. I apologize. I'm having some trouble with my computer right now. That's 5/2. Okay. But again, it worked because I focused on the odd power and I pulled one of those out for my du. Now don't forget that that problem also had that interval on it, right? It was pi sixths to pi thirds. So we ignored that through the integration because we don't need it, but now we need it. So the answer was 2 sine to the 1/2 x minus 2/5 sine to the 5/2 x between pi sixths and pi thirds. That's all. I mean, it's a little insignificant. It's just evaluating, but still, you have to do it. So you plug in the pi thirds, you plug in the pi sixths, and so we end up with 2 times sine of pi thirds. Sine of pi thirds is square root of 3 over 2 to the 1/2 minus 2/5 times square root of 3 over 2 to the 5/2 minus 2 times sine of pi sixth, when I plug in my pi sixth in here, is a half. So a half to the half. Plus, now this will become 2/5 because I'm subtracting it, so plus 2/5, 1/2 to the 5/2. So it doesn't look nice, but you can plug it in, you can evaluate it. There's really not a whole lot more. I mean, we could simplify this down some more, but it's not worth the time to do right now, in that this is the answer. The best I think we could probably try to do here would be to maybe rationalize, would be write this as a single fraction possibly. If you notice, if this is to the 1/2, I can write the numerator and denominator all to the 1/2. Same thing here, 5/2. But again, not worth your time. This is not the important part of this problem necessarily. If you had this as a test question, you left the answer like that, I'm fine with it. But I didn't want to forget the pi sixths and the pi thirds that was in the beginning of this problem. Now, you're not always going to have odd powers to work with. Like, those are optimal. It's great. Those are the ones that work out the nicest. But you're not always going to have odd powers to work with. So what we're going to want to do is we're going to say, well, what if we have an even one? And here's an example of that. In this case, all I have is a cosine. I don't even have any sines. So I have cosine to this even power. My only way to do this is to use the power reducing identity, which was cosine squared x equals 1 plus cosine 2x over 2. So what I'm going to do is I'm going to write this as a square. Well, I can write it as 2 squares. So I get, if my computer will work, here we go, cosine squared x times cosine squared x dx. And I'm going to apply the power reducing identity here and here. And so I get 1 plus cosine 2x. This is frustrating. 2x over 2 times 1 plus cosine 2x over 2 dx. Now to go from here, we got to figure out, well, what am I going to do? Well, the only thing I really can do is to distribute all this out. Okay. In the denominator, it's 2 times 2, so 4. So I'll pull the 1/4 all the way out to the front. And here I'm going to have 1 plus 2 cosine 2x plus cosine squared 2x dx. All right. So now what? Well, I got to integrate 1 with respect to x. That's easy. I got to integrate 2 cosine 2x with respect to x. That's easy. But then I have to integrate cosine squared 2x. Well, the problem with that is it's a power bigger than 1, and it's an even power. So what should I do? You guessed it. Power reducing again. So I'm going to rewrite this using the power reducing identity. So I have this 1/4. I have 1 plus 2 cosine 2x plus, now this is going to become 1 plus cosine 4x over 2 dx. Now why the 4x? Because this x is just this arbitrary thing. You call it a theta, call it whatever you want. Whatever this is here inside the cosine squared has to be multiplied by 2. So if it was a 2x already, it now becomes a 4x. Very simple. All right, almost there. One more step and we're ready to integrate. So I'm going to write this as 1/4 times the integral of 1 plus, I'm going to split this fraction apart into 1/2 and cosine 4x over 2. Well, the 1/2 and the 1 can come together. And I'm going to write this now as 1/2 plus 1 is going to be 3/2 plus 2 cosine 2x plus cosine 4x over 2 dx. And now I'm ready to integrate. I got 3/2 with respect to x, easy. Cosine to the first, cosine to the first. So finally, what do I get? I get 1/4 times the integral. Oh, no, I'm already integrating. I get 1/4 times 3/2 x plus integral of cosine is sine, but now integral of cosine 2x, so I have 2 times sine 2x over 2. So then these will cancel. Plus, I'll do the same thing here. This is going to be 1/2 because of this. And then I'll have sine 4x over 4. And then I have a plus c. So all I really have to do is multiply these together, cancel these 2's, and I have my final answer, which I'm going to write. This is not going to look great, but I'm going to write it here. So I'm going to have 1/4 times 3/2 x plus sine 2x plus sine 4x over 8 plus c. And there's your final answer. And you see that the even power one's definitely a little bit more involved than the odd ones. But if you just keep applying your power reducing identity till you get to either first powers or odd powers, then you're ready to go. If you get an odd power, then we go back to what we did before. If we get a first power, then we're good to go. And if we get an even power, we reduce it some more. So the last example brings up a fairly simple formula called Wallace's formula. In all honesty, you're not going to be using this a whole lot. You don't have to commit this formula to memory or anything like that. It's just that certain integrals have a pattern to their answer. So it says if we were doing cosine to a power, x dx, okay, and that integral was being evaluated between 0 and pi halves, there's a pattern to the way the answer is going to develop, depending on what that power is. If the power is odd, 3 or bigger, this is the formula for how we would generate the answer. If the power is even, 2 or bigger, this is it. So the last one we did was 4. Okay? So it's even, so it's here. So what it says is that we should have an answer of 1/2 times 3/4 times 5/6 all the way up to n minus 1 over n times pi halves. Well, again, n was 4, so we're actually going to stop here, so this won't be here. Right? So it'll be 1/2 times 3/4, and we'll stop because that's the power. Okay, if we were going to keep going, if it was any even higher than that, we'd go up to 6 or 8 or whatever, but stop there, times pi halves. So ultimately, what do we get here? We get 3 pi over 2 times 4 is 8, times 2 is 16, There's our answer. Now, if you look at the answer that we had a second ago, it was 1/4 times 3/2 x plus sine 2x plus sine, 4x over 8. If I evaluated that between 0 and pi halves, we're going to get this answer. But the reason why there's a pattern to it is the way that this answer would create the same pattern over and over again as that power gets bigger and bigger and bigger. So if I plug pi halves in here, here, and here, okay, and then plug 0 in here, here, and here, you see what we end up with. So if we plug pi halves in, we're going to get the 1/4 times 3/2 times pi halves plus sine of pi halves, or 2 times pi halves is pi, and sine of pi would be 0. If I plug pi halves in here, 4 times pi halves is 2 pi, sine of 2 pi is 0. Minus, if I plug in 0 here, here, and here, same deal, 0 across the board. So if you look at all these zeros, what do you really end up with? What we had here, and we get this answer. So it's just Wallace was a mathematician that noticed that as the power gets bigger, there's a pattern to the answer on the interval between 0 and pi halves. Same thing goes for odd ones. So there is, that's interesting. I'm not sure how consequential it's going to be for you, at least in the near term. So it's not worth memorizing, but just something I point out. So now we move on to the secant tangent questions, where secant is raised to a power and tangent is raised to a power. We're going to approach these fairly similarly in that we got to save our du. The problem with that is that the derivatives are a little more complicated when it comes to secant and tangent than they are for sine and cosine. We're only going to really need one identity, and that's that 1 plus tan squared x equals secant squared x. Okay. Basic Pythagorean identity for tan and secant. So that's it. And we're going to take it to the same approach. Now the problem here is with the derivatives. So the derivative of sine is cosine and cosine is sine, barring a negative, right? But generally they're derivatives of each other. That's not the case with secant and tangent. Secant's not the derivative of tangent, tangent's not the derivative of secant. They're related in some ways, but not the same. So let's just say I give you this example. Integral of tan to the, doesn't really matter what power, 10th x times secant squared x dx. Well, this example is very easy. It's very easy in that I have a u and a du already. Secant squared is the derivative of tangent. And so I have, very similar to the very first problem we did today, is it's already set up. This is something you could have done in Calc 1. U is tan x, du is secant squared x, and this integral becomes the integral of u to the 10th du, which you can then do. But what if this was not secant squared, but secant to the 5th? Now none of this works. So the goal is, can we get it into something like this? Well, we would have to save a secant squared for my du, or if we did it with the other way, think about what the derivative of secant is. If you think about the derivative of secant, it's secant x tan x. So I'm going to want to save secant x tan x for my du. So what you're saving to be your du is a little more complicated with these examples, which makes them a little harder. But we take the same approach. So let's look at this. Option 1. Power of secant is even and positive. If you have an even positive power for secant, what you can do is you can save a secant squared factor for your du, and then that means everything else has to convert to a tan, so that you can do basically what we did here. So let's think about this. secant is to an even power. I can always write an even power as an even secant squared. It can be pulled out, and I can be left over with another remaining secant there. So if everything else has to be related to tangent now, well, the remaining secant that's left over can be written as a secant squared. That secant squared can be used in the Pythagorean identity. So now I have all tans and a secant squared. I have my u's and I have my du, and I'm ready to go. So in that case, u would be tangent and du would be secant squared. And it looks a lot like what we did with sine and cosine. Option 2. Option 2 is that the power of the tan is odd and positive. So if the tan is odd and positive, what you're going to want to do is you're going to want to save a secant and a tangent factor for your du, in which case you have to convert everything else to secants. So odd positive power for your tan, save one of those tans, and pull one of these secants out. So that means the secant is now one less than it was before. The leftover tans can be written as a square, and so you have a secant tan saved. The tan squared is turned into a secant using the Pythagorean identity. The leftover secants, along with these secants, are all your u. Here's your du, and you're good to go. Those are the most basic ones. Then they start to get a little bit tricky from there, similar to sine and cosine. Let's get rid of some of this color. All right, let's see what we got. So, third scenario. There's no secant factors at all, and the power of tan is even. So it's a pretty specific scenario, but nonetheless, something we can do. Convert a tan, this should be squared. Convert a tan squared factor to a secant squared factor, okay, by using the Pythagorean identity. Then expand and then try and repeat. So the idea is you're trying to make a secant squared show up for your du. So we take a tan, okay? We're going to pull a tan squared out of that tan. So you have the remaining tans here. That tan squared then turns into a secant squared minus 1, and then we work with that in terms of our u and our du as best we can. Another possibility is the integral is in the form of just a secant, and that power is odd and positive. Well, we saw one of these in the last lesson. These are going to be integration by parts, and that's where the original integral is going to pop back up again. If none of this works, if none of these scenarios work for you, the last resort is to just convert everything to sine and cosines. Secant can be written as a cosine in that secant x equals 1 over cosine x, and tangent is sine over cosine. Convert to sine and cosine, and then revert back to what we did previously. I don't suggest you start with that, because sometimes you're making your life harder than just maybe looking at some of these other scenarios. But if you're looking at a problem and you say, I have no idea what to do here, try this. Okay, try convert to sine and cosine and see how it goes. So let's do a couple of examples. Again, all this is all about practice. The more of these you do, the easier it'll get down these different steps. There's definitely a lot more options when it comes to secant and tangent because the derivatives are a little bit more complex. But the more of these you do, the better you'll get. So just try and identify the powers. Secant is even positive, tan is odd positive, etc. and go from there. So you look at this, the first thing you should see is tan is to an odd positive. Secant to the 1/2, which is something you ignore right away. So what we need to do is we need a secant tangent saved for my du. So I'm going to have to rewrite this as tan cubed x times secant to the minus 1/2 x dx. Then I'm going to pull out a secant x, and a tan x for my dx. That's my du. Well, if one of the tans is pulled out of here, it's a tan squared. And if one of the secants was pulled out of here, what would be left? Well, it would be secant to a power such that when I multiply this secant back in, I get minus a half. So that would have to have been minus 3/2. Now the remaining tangent can be written in terms of secant as well. So I end up with secant squared my x, don't forget your x, secant squared x minus 1 times secant to the minus 3/2 x times secant x tan x dx. So here's your du. And I'm going to distribute this in here just because I think I'm going to need it later anyway. I think, like I said before, with the other ones with sine and cosine, I don't have to. I can wait, but honestly, eventually you're going to need to do it anyway, so let's just do it now. So I get secant squared times negative 3/2, add those exponents, you end up with 1/2 x minus secant to the minus 3/2 x times secant x tan x. So if this is my du, what's that the derivative of? Well, secant. So there's your u. U is secant. Du is secant x tan x dx. And you simply just get u to the 1/2 minus u to the negative 3/2 du. So simple power rule integrals. This one will be u to the, add 1, so 3/2 times 2/3. This one will be u to the 1 minus 1/2, so this will be plus 2u to the minus 1/2 plus c. Replace your u in, and we're done. So 2/3 times secant to the 3/2 x plus 2 times secant to the minus 1/2 x plus c. That's it. It's a pretty easy one. But because we identified what we had in the power and what we needed for our du. Here's another one. Now, if you notice in this one, tan is to an odd positive power. So we could approach this one the same way we did the last one. However, secant is to an even positive power, and we had a technique for doing that as well. In this one, it doesn't matter which one we use. We'll be correct in our final answer either way. Since we just did a tan to an odd positive, we'll focus on the fact that secant to an even positive. Also notice that I have a 3x here and here. There's not much concern there. It changes things a little bit in the 3 is just going to be involved throughout our problem, but it doesn't really make the problem all that much harder. The one thing to note is that these 3x's have to be the same. I can't have a 3x in this one and a 5x in that one and have this work out. Much, much more complex problem, which we will not be dealing with right now. So as long as whatever's inside these functions is the same, we continue on our process. All right, so I'm going to focus on the fact that secant is to an even positive power. So what we do with those is we have to pull out a secant squared for our du. So I have secant squared 3x, tan cubed 3x, and secant squared 3x dx. So this one saves from my du. I still have secant to the 4th because the square and the square is really the 4th. So now what I have to do, if that's going to be my du, all of this has to become tan. So this one has to convert to a tan, and since it's a square, I can use the Pythagorean identity. So I end up with the integral of tan squared 3x plus 1 times tan cubed 3x times secant squared 3x dx. And then I'll distribute this in here and here, okay? Just like we've done in all the previous ones. So then I'm going to get a tan to the fifth 3x plus a tan to the third 3x, and then a secant squared 3x dx. You notice the 3x really hasn't played a huge role. I just keep writing it over and over again. Here's where it plays a role. Remember, this is my du, so by default, u would have to be tan, but tan 3x, so that the derivative would be 3 secant squared 3x dx. And that's just using your chain rule. That's where the 3 comes from. Now, we don't have that extra 3, so I'm going to have to divide by it to move it over. But secant squared 3x is what was going to come out of the derivative of tan 3x. So that's the only place it comes into play. So this extra 1/3 is where what results from the 3x. So what do we end up with here? We end up with 1/3. That's from the du of u to the fifth plus u to the third du. This is just here. So once you have that, then it's not that much. So 1/3, we end up with u to the sixth over 6 plus u to the fourth over 4 plus c. Resubstitute. I'll multiply this 3 through the denominator. So I end up with tan to the sixth 3x over 18 plus tan to the fourth 3x over 12 plus c. And there's your answer. Okay. Again, I could have done it with tan to the odd power. My answer would have looked different because of how I would have assigned my u's and my du's. Not that the answer is wrong, it's just a different form of this answer. Here's an example where tan is even and I have no secants. So what I need to do is essentially make secant squared show up so that I can try and get a du to show up out of this thing. Oh, I got the 0 and pi fourths here as well, and we'll handle that at the end. So I'm going to rewrite this. Let's get a darker color as 0 to pi fourths tan squared x times tan squared x dx. Now, one of these tan squares I'm going to write as a secant squared, so I'll do that there. So I'm going to write this as the integral from 0 to pi fourths of tan squared x times secant squared x minus 1 dx, and distribute this in here and here. Now, in doing so, I end up with the integral from 0 to pi fourths of tan squared x times secant squared x minus tan squared x dx. Now, this piece is set up perfectly. If u is tangent, du is secant squared. So I got a u squared du. This one, however, is tan to an even power. And it's tan to an even power without any secants, which is basically what I had in the beginning. So do it again. Somehow get the secants to show up. Well, you got to write this as tan squared. It already is. Apply the Pythagorean identity and then go from there. So I have 0 to pi fourths. I have tan squared x, secant squared x still, minus tan squared will be secant squared x minus 1 dx. So this negative can distribute in here and here. I can integrate each one of these separately. This one, again, is going to be u squared du. So I'll end up with u to the third, so tan to the third x over 3 from this integral. This is the integral of secant squared, which is tangent. And this is the integral of positive 1, which is just x, between 0 and pi fourths. And that's it. So now we just plug in pi fourths. Well, you got to remember, the tangent of pi fourths is 1, and the tangent of 0 is 0. So if you remember that, then this is going to be 1/3 minus 1 plus pi fourths, sorry. And then this will be, when I plug in 0 here, I'll get 0, 0 here, I get 0, 0 here, I get 0. So ultimately, this is my answer. So I'll end up with pi fourths minus 2/3. And I'll leave my answer like that. All right, here's one more. In this one, it doesn't really fit any of our categories. Because if I rewrote it as secant x tan to the negative 2x dx, which is the form we originally start with, it doesn't really satisfy any of those different conditions that we talked about. So push comes to shove, you have no other options. Let's just switch to sine and cosine and see if we can make it work that way. And so we're going to write this as 1 over cosine x over sine squared x over cosine x squared x dx. And this is for secant, and this is for the tan squared. So fraction divided by fraction, I flip and multiply. What I end up with is 1 over cosine x times cosine squared x over sine squared x dx. Well, that'll allow me to cancel this at one of these. And I can rewrite this as sine to the negative 2x times cosine to the first x dx. But notice, I got it to a cosine to the first x, which takes us back to where we started. U du. So if u equals sine x, du equals cosine x dx. You simply have the integral of u to the negative 2 du, which would give me negative u to the negative 1 plus c. So I can write this as negative 1 over sine x plus c. But 1 over sine can also be written as cosecant, so I could write the answer as cosecant x plus c. While this is acceptable as a final answer, just note that this is the same answer in a different form, something I've been talking about a lot now. That happens with trigonometric expressions. You can write it in different ways. They may look different, but they are equal to each other. One last thing we need to talk about, and it's something I brought up in a previous example, is what about when these inside pieces that the sine and cosine or secant and tangent are working with are different, okay? Well, we're fairly limited in what we can do, but we do have a couple of identities, and they're called the product of sum identities. So we have a few product of sum identities as relates to sine and cosine on how to deal with this. So if we apply one of these identities to this, it has nothing to do with the power thing we were just talking about, but it comes up in relationship to one of those previous examples where we looked at secant and tangent that had 3x inside of them. So in this case, they're different, right? They're different. I can't just go ahead and start doing, say, u and du. It doesn't work, because if u is sine 5x, du is going to be 5 cosine 5x dx. I don't have a cosine 5x, I have a cosine 4x, so that doesn't work. So what I have to do is I have to use one of these identities. So in this case, I have a sine times a cosine, which is this one. M is 5, N is 4. I apply this identity and then integrate the resulting piece. So it would be 1/2 times sine of m minus n, so that would be 5 minus 4, so 1x, plus sine of m plus n, so 5 plus 4, so 9x dx. Now, this is definitely something I can integrate, because now I don't have any cosines, I just have sine, both to the first power. So I end up with 1/2 times, integral of sine is minus cosine, and minus cosine 9x over 9 plus c, and it's done. But it needs to be stated that, this complicates things far more than the different powers complicate things. So if I have sine to the fifth x, cosine to the fourth x, that's not too bad. I mean, we can deal with it. Powers are different, but at least the thing inside the functions are the same. When these angles inside the sine and cosine are not the same, that's when things get worse. Yes, we have some product of sum identities we can try and use, but they're very limited. Notice both sine and cosine are to the first power. So, you could see if we start introducing powers into this, it just becomes something that's not worth working with right now.